This is a ball. This is a ball. And it has some mass, but we don't care about the mass, not yet anyway. And we're going to drop it from this cliff, and we'll say the cliff is 120 meters high. And I want to know, say, how long is it in the air? Or how long does that thing take to get down to the bottom of the cliff? Well, just like in your kinematics problems, write down what you know. There's 5 possibilities. You can know VI, you can know VF, you can know time, you can know change in position, or you can know acceleration. As soon as you know any 3 of those, then you can solve the problem. So do we know initial velocity?
Yes,
0. Dropping it from rest. Do we know the final velocity?
No.
No. Whatever the velocity is down here, we are not sure. Yes. We don't know final velocity. Do we know time?
No, that's alright.
That's what we're looking for. D?
120.
Actually, negative 120 meters. We are finishing below where we started. We're going down 120 meters. So using our same scale here, this is going to be down. And what's our acceleration?
920 meters per second.
And that is also going to be downwards. Gravity sucks down towards the center of the earth. I don't know. That's just how you say it. You've got a person standing on the earth. This is the earth, by the way. They're going to be accelerated towards the center. Over here, they are going to be accelerated towards the center. Gravity always acts directly downwards. There's no situation where gravity does not act downwards. So since gravity is down, it will have a negative value. We know 3 things, so we can solve for time. What do you want to use?
V equals delta D equals VIT plus 1/2 AT squared.
Delta D equals VIT plus 1/2 AT squared. If you try to use any of the other ones, you'll get stuck with final velocity. So delta D is down 120 meters. Initial velocity, 0. 1/2 the acceleration, -10 meters per second squared times time squared. 120 times 2 divided by 10.
24.5.
And T is 4.9 seconds is equal to T. A different type of problem. How high do you want the cliff to be?
5 meters.
Okay. What do you want the velocity of the ball to be?
3.
And what do you want to solve for?
Acceleration. Oh, no, that's kidding. I guess final velocity. That's the only other.
Okay. Where do you want to solve for final velocity? Here, 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 here. Where do you want?
When it gets to the Olympic cliff.
When it's the ground, perfect. Good.
Why'd you say that's the right one?
You'll see. We'll do that one too. So, in a problem where you're going in two directions, so this ball is going to be thrown up and then it's going to come straight down. Identify the points of interest for us. The first one is where we start, the second one is where we finish. If we had wanted to know the final velocity here, then we would have finished our problem there. It's important to note where you're starting and where you're finishing before you start the problem. Final velocity is what we're looking for. Other things that we could possibly get are these. Do we know the initial velocity? 3 meters per second, positive or negative? Positive, it's going up. Acceleration? Negative, because acceleration always goes down. Time?
Don't know.
No, change in position.
8.
Negative 5 meters. Regardless of what's happening between this point and this point, we could care less.
Oh, okay.
All we care about is what's here and what's
This is
here.
initial and final.
Right, this is displacement that we're looking at actually. So the displacement of this ball is going to be down 5 meters, regardless of the path, that's what it takes. Now we know 3 things, we can solve for everything else. What equation looks tasty?
The one without time.
The one without time, which would be df squared equals vi squared plus 2a delta d. And then plug in the values that you know and what you don't know. Final velocity squared equals our initial velocity squared. That's twice our acceleration. Times our change in distance. Three squared.
9.
5 times 10.
That side equals 1.
50 times 2, 100, and 9 plus 100, 107. 109. And the square root of 109. 10.4 meters per second. Good?